Okay guys, as requested, maybe not as requested, but anyway, here we're going to start talking about EM induction, electromagnetic induction. So EM induction is when an electric field and a magnetic field kind of move or shift past each other. One induces the other one. So here we're looking at moving magnetic fields and how they can actually be used to generate electricity. So the magnetic flux is this guy here, is defined as the magnetic field strength over an area perpendicular to a shape or a surface. So we're looking at, remember the right hand rule is we're looking at sine theta being maximised. So here we're looking, it's all right angles, perpendicular stuff. So the magnetic flux is defined as magnetic field strength over an area. So it's a really difficult idea to get your head around, but I guess the way I think about it is the amount of magnetic field flowing through an area. Alright, and a dude called Michael Faraday, Google him, fantastic guy, came up with, and what's now known as Faraday's law. You can induce an EMF. An EMF is electromotive force, or a voltage, is able to be generated by changing the magnetic flux over some sort of amount of time. So if we get our magnetic flux, which is this guy up here, and we change either the magnetic field strength over time, or we change the area that it's in over time, so we basically make a magnet move. So this is if we change the strength, we change the size, we change the direction, we're changing the flux. So if we can do any of those things over time, we're going to generate an EMF. So if we have a loop like this guy here, and we've got a magnet, north pole here, magnetic field going that way, if we move this magnetic field near this loop, what we're actually going to do is generate an EMF in that loop. And now that EMF is going to be generated simply because we're changing the flux over time. So if we make this magnet move super fast, so we're making big change, small amount of time, we're going to induce a larger EMF. If we make it move really, really slowly over a long time, smaller number on the top, bigger number on the bottom, a much smaller EMF. Now, if I was to get 2 or 3 of these, I'll mess up my drawing. Actually, I'll do it down here. If I was to get, a few of these loops like this, and I was to have the same magnet move that way through there, what I'm actually going to do is induce an EMF in the first one, and the second, and the third, fourth, fifth, etc. And all of these EMFs are unique. Now, if I was able to get these EMFs, get these loops, and say join them together, now what I can do is get those electromagnetic force, those voltages, to piggyback on top of each other. So this works really well, and you guessed it, a solenoid. So if I can make the magnet move through that solenoid, it's moving through a whole bunch of loops, just like this one. Each of them has an induced EMF in it, so we're actually building and building and building. So we can end up looking at the the EMF in a whole bunch of loops as delta phi over delta t, so the change in flux over time multiplied by the number of loops that it's actually gone through. The last part that I want to talk about is to do with Lenz's law. So Lenz's law was in the exam last year, and it was kind of horribly done because it was brand new, and it is kind of a little bit of a messes with your head a fair bit. But what we're looking at is Lenz's law tells us which way this EMF is going to be induced. So here's our magnet, and we're going to change the magnetic flux through this loop, and the magnet's going to move this way through the loop. Now, we don't know if the induced EMF is going to go this way or this way, so we can't really tell what's going to happen without Lenz's law. Lenz's law says that the induced EMF is going to go in a direction that opposes this magnetic field. So I want you to think about it in terms of ignoring this whole setup over here. So we're going to ignore the fact that there's actually a magnet at all. If I make a current move in a specific direction, so if I make the current flow this way, what we're actually going to have happen is a magnetic field is generated like this. Okay, so we're going to generate a magnetic field. If I was to move the current in the opposite direction, the magnetic field would change direction. So let's say I get my magnet and I'll put it here and I'll make it go through the whiteboard. Now the X's mean that the magnetic field is going into the whiteboard. If I make this magnet move into the whiteboard, now I'm adding magnetic fields on top of each other. Lenz's law says you can't do that. It says that the induced EMF in these little guys here, in this loop, sorry, is going to go in a direction so that it opposes the magnet that caused it, or the magnetic field, or sorry, the changing magnetic field, the flux, the changing magnetic flux that caused it in the first place. A really interesting way of looking at this is in induction hot plates, or your wireless charger on your mobile phone, similar sorts of ideas. So what we're looking at is swells of current that are induced in something like this. So here's our massive big steel plate, and we're going to have a magnetic field like this. And because it's we're going to change this, we're going to change the strength of the magnetic field going into the board, or we can completely change the direction entirely. So we can make it into the board, then out of the board, then into the board, then out of the board, and so on and so on. So what actually happens is, if we were to zoom in on each of these microscopic little sections of the board, we would actually find that depending on which way the flux is changing, we get these tiny little swirls of induced EMF in that metal plate. So you put your metal saucepan on top of an induction hot plate, and this is what happens. The induction hot plate induces an EMF in the bottom of the saucepan, which creates these moving swirls of EMF. These moving swirls are moving charges, moving things are hotter, therefore we get a build-up in heat, build-up in temperature, and that's how an induction hot plate works. We have these swirls, tiny little things. If we were to make currents move in straight lines, that's nowhere near as efficient energy-wise, and these are called eddy currents. Okay, they are tiny little swirls or loops of electric current in a plate or in a surface like this that move in a direction that opposes a change in magnetic flux that caused it, based on Lenz's law.